All right, so in order for a relation to be a function, remember this. Every output, sorry, every input must have one and only one output. Okay, so let me give you one that it is. I'm going to give you some inputs. So let's say your inputs, or if you want to call them the x values or the y values, and another name for this, all the domain, right? You got to know this too. And these are your range. So they all mean the same thing. So in the input section, I'm going to input the numbers 1, 2, 3, 4. And we're going to put them in this function, right? I don't know, multiply by 3, add 5, multiply by 10, subtract 4, or whatever function it is. So when you input the 1 and something comes out, and I'm just making this up, it comes out as 7. When you put in a 2, it comes out as 9. When you put a 3, it comes in at 11. And when you put a 4, it comes out as 13. So notice that when I input the 1, I only get one output, which is the 7. One and only one output. When I input the 2, it comes out as a 9. When I input a 3, it comes at 11. And when I input the 4, it comes at 13. So 1 has only one, I guess, remember the example of partners. 1 has only one partner, which is a 7. No one else. He's loyal to 7. And so is 2 loyal to 9, and 3 is loyal to 11, and 4 loyal to 13. So explanation here, you can repeat this. Every input has one and only one output. Now, let's describe a relation that's not a function. Well, let me select the same guys here. The 1, the 2, the 3, and the 4. 1, you put in 1 in the function, right? And it comes out as a 7. But the 1 also comes out as a 9. The 2 comes out of a 13. The 3 comes out as a 15, and the 4 comes out as a 17. So when I input 4, it comes out as 17. And when I input 3, it comes out as 15. When I input 2, it comes out as 13. And then, but when I input a 1, it came out as a 2 and a 7. So remember, every input must have one and only one output. So the problem here is that 1 has two outputs, 7 and a 9. So not a function because the input 1, or the x value 1, input 1 has two outputs, right? It has 1 and 7, and then it has 1 and 9. And that is not allowed, so not a function. And that's an example, okay? On to the next one. In a graph, we can do the vertical line test that we were talking about. So let me create a graph here. Create that graph. A line, and then if you do the vertical line test, let me create a line here. Let me change color. So let's say you had a graph like this, right? And you want to see if this is a function. Well, in order for this to be a function, if you do the vertical line test, you take a vertical line and you move it across this line. And notice that the blue line will only make contact with the red line at one point as it moves along from left to right. Okay, so nowhere will this blue line, the red line, meet in two places. Okay, so that's an example. The line doesn't have to be a red line, so a straight line. So let me erase this. All right, so let me erase this. Give you a different example. So let's say you had a Line that looks like that. I'll do a vertical line test. As I move this vertical line across that function, does it make contact in only one place at any given point in time? Yes, it does. So this is a function. This is a function because it passes the vertical line test. Now, over here, I'm going to draw something that's not a function. And I'm going to take a vertical line again. And let me just fix this a little bit. It's a little too vertical for me. I take this line, and bring it over. And notice that as I move this line here, it makes contact here. Change colors. Change color here and here. So at this particular point, look, and let me make it a little bit better. Move that line to a value that I can actually, let's say right here. So it makes contact here. Right, it makes contact here. It makes contact here. So at -3, so if we create a value here, table of values x and y, notice that at -3, when x is -3, y can be -3 and y can be 6. So -3, so if we create a mapping diagram, I think it's always easier to see. -3, right, our x values, has an output of -3, which is right here. And it also has an output of +6, which is right there. And this obviously is not a loop, right? And instead of doing this, the table and the points, and we can just easily take a vertical line and move it across, right? And notice that it fails all these spots here as I move the blue line, vertical line across that function. It fails because it's meeting, look, in two different spots at the same time. So the x value at that particular point has two y values, and this not a function because it fails the vertical line test. Okay. So I drew one that was a function. I drew one that was not a function. Okay. And again, let me get over here and erase this and give you another one that is a function. So if you wanted to draw a line, then look, this one, clearly a function, because as you move this vertical line across the purple line, you notice that it makes contact in one spot. Only the blue and the purple meet at one location only, no matter where you go. Okay? Moving on to the next. Here, create a table, right? So this is no different than when I created the earlier mapping diagram this way. So instead of, I guess, 2 circles, and I did 1, 2, 3, and then I did 7, 8, 9, right? I can do the same thing here. So values. So let's say there's x values of 1, 2, 3, and 4, and then you put the 1 in the function, and it spews out. 5 comes out, 10 comes out, 15 comes out, 20 comes out. So for this particular function, for this particular relation, every time you put a 1, 5 comes out. Every time you input a 2, a 10 comes out. And every time you put a 3, a 15 comes out. And every time you put a 4, a 20 comes out. Because the function, the rule here is going to be 5x, right? So every x value gets multiplied by 5. There's no way I can put 1 in here, right? 1 in this rule here. There's no way I can put in and come out any different. So again, every x value has only one y value. And then a relation that's not a function, again, let me just write the numbers down. 1, 2, 3, 4, and let me create a function. This is a 5, sorry. Gotta correct this. So 1, 1, 2, 3, for example. So here we have a function, and when you enter 1, it comes out as 5. When you enter 1 again, it comes out as 10. When you enter 2, it comes out as 15. When you enter 3, it comes out as 20. So the problem here is that when you entered 1 in this function, you got a 5, and when you entered 1 again, you got a 10. So not a function, right? Because as you noticed, and then if I draw this way, I think it's always easier. Here we have the numbers 1, 2, and 3, right? Remember, this is also called a domain, and these are called a range, so just for you to get used to. If you want to call them input, output, you can do that too. So the problem here is that when you input a 1, you got a 5 and you got a 10. So notice that the 1 has 2 partners, not allowed. You should only have 1 partner, right? The x values should only have 1 partner. So 2 has a partner who's 15 and the 3 has a partner who's 20. And just to make it, just to give you different examples, let me go back here. All right, let me create another mapping diagram here. Let's say I had 1, 2, 3, 4, right? My x values, my y values, and when I press 1, I get a 7. When I press 2, I get a 7. When I enter 3, I get a 7. When I enter 4, is that a 7? Now, would this be a function? Does it follow this rule? Every x value. So does the 1 have 1 and only 1 y value? 1. So ignore everybody else. Just think about the 1. The 1 has 1 partner. The 1 partner is up with 7. Does the 1 partner with anybody else? No, it doesn't. The 2, who does it partner is? With 7. The 3 partners with 7. Doesn't matter that they all the x values partner with the same y value, right? If you read the statement again, 1 has only 1 output, 1 value, and the only value that it's the output of for 1 is 7. Okay. Whereas this, right? Notice that this is a little bit different, right? So 1 is 7 and 1 is 9, for example. This is definitely not a function because this input here has 2 outputs. And again, interchangeable, right? So okay, so this can be called the input, can be called the domain, and called the x values. The other one's called the output, the range, the y. Okay. I'm gonna skip this part here because we haven't got to that, and then we're gonna go to this one. So determine if this graph represents a function, and we can use the vertical line test, right? So which is the easier way, the cheating way, I guess. And then we're gonna take this and move it across that line there, and notice that the purple and the function there only meets in one location at all points in time. So this is a function, okay, because it passed the test that we are doing right now. This is called a vertical line test. You take a vertical line and move it across, right? And if you notice, the purple and that black line only meet in one location. So this is a function. It passes the vertical line test, right? Which is just an easier way of doing. So in here, instead of doing the vertical line test first, I'm going to plot the points here. So let's take a look at the points. So let's take a look at these points right here. I'm going to change colors. This point right here. Right, at that point in time, we have that x, let me create it, well, 1, right, there's a point there called 1, 1, right? And there's a point right under it called 1, negative 1. So 1 goes with 1 and 1 goes with negative 1. Let me take this point here. The second point is called 2, 2. And the point right under it is called 2, negative 2. So if I were to do microdragon, so 2 has an output that's called 2, and 2 has an output that's called -2. So this does, it's not a function, right? Because every input has more than one output. Look, 1 has more than one partner. One partners up with 1, and one partner up with -1. 2 partners with 2, and 2 partners with -2. Not allowed. Right, so, but instead of doing that, if you do the vertical line test, right, that's why we do the learn, to save us from writing all that, and we just move this line across and say, hey, look, it touches the purple line 2 locations, touches the purple line 2 locations, 2 locations, 2 locations. So this is definitely not a function, fails vertical line test. Go to 3. Does this pass the vertical line test? So there's my line. Good, 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 good. So far, so good. So far, so good. So far, so good. And right here is the first time it fails. Notice that it touches the purple line in here and in here, 2 different locations. As I move it, right, look, again, it touches the purple line in 2 different locations. That means that that particular x value has 2 y values. So, again, fails vertical line test. Let's move this to this one. I already have it. Good, 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 good. As I move the vertical line across that, across the graph here, does it touch? We're not counting the x and y axis, but we're just talking about that graph, that line there, right, that function. And notice that it only touches the purple line at one given point in time. So this one is a function, passes vertical line test. It's a function. Next one, looking at a table. Again, so by looking at a table, right? Again, nothing complicated. So notice we got to look at every x value. So 0 has an output -13, 1 has an output -28, 2 has an output to -28, and 3 has an output -5. This is a function, right? Every single x here. I know that you're thinking that maybe the 1 and the 2 share -8, but that's okay. 1 has only one partner, which is -28. That's it. 1 has no other output except -28. 2 has an output of only -28. It doesn't matter that the 1 also has an output -28. It doesn't matter. Just look at 2. Are there any other 2's? No, indeed. For x values, are there any other 2's? No. So as far as we know, anytime that you input 2, a -28 comes out. And only -28 comes out when you input a 2. So it's a function. It is a function because every input has one output. Here, definitely a failure. So again, let me transfer this information to here. Let me call this domain. Domain is all your x values, and range is all your y values. Right? So we're writing x and y. I'm just changing so that you get accustomed to it. So for domain, I'm going to write the 2, and I'm only going to write the 2 once. Don't repeat it. Right, so it's the only one x value, the 2. The problem is the 2 partners up with 5, partners up with 6, partners up with 7, partners up with 8. In other words, the 2 has 4 different outputs. Right, so imagine there's a machine here. As the 2 is going along in here and enters, right, it comes out with 4 different outputs: 5, 6, 7, and 8. So therefore, not allowed and not a function, because the x value, because the output, because the input 2 has more than one output. Okay. Again, more tables. So this one, again, think about this. When you have an input of 5, you have only one output. Yes. 5 has no other output except -10. This is a function. Okay. Is a function as every input has one output. Okay. Nothing else comes out when you input 5 except -10. -3 has an output of 0, -2 has an output of -1, -1 has an output of -2, 0 has none. Do you see any repeating values in the x? No, so we have only one -3, only one -2, only one -1, and one 0, right? So, and for each, what we can say is a function as each x value has only one output. Now we're looking at mapping diagrams here. I think it's easier to see if this is a function, and I like this. So clearly here we have a problem. Let me write domain. Let me write range. Right? So if you want, these are your inputs and these are your outputs. This is clearly not a function. Not a function because 2, because the input 2 has 4 outputs. Oh my god, 4 outputs. Right? It points out 6, it points out 7, it points out 8. Sorry, 3 outputs. Okay. Next one. Let's see. -6 partners up with 4. That's okay. Do we have any other -6? No. -5 partners up with only 2, and -4 partners up with only 3. So this is a function. One output for every input, right? So every x has only one part, boyfriend, girlfriend. -6 is only dating 4. -5 is only dating 2. -4 is only dating 3. That's it. Everybody's boring. Okay. 11. Let's see here. 6 is dating -4, so that's okay. 17 is going out with 4, that's okay. 28 is going out with -4. And 39 is going out with 4. So look at it each individually. So 6 is only partnered up with -4. True. There's nobody else 6 is going out with. 17 is only going out with 4. Also true. 28 only going out with -4. True. And 39 is only going out with 4. So each x value has only one y value. Okay, so this is a function. Okay. This one, problem right off the bat. 0 hangs out with 4 and 0 hangs out with 2. Not allowed. Every input, right? These are my inputs, my x values. They only should be hanging out with one person. There should be only one output. So if 0 only had an output 4, that'd be a different story. And likewise, 2 has an issue here because 2 is 5, and then 2 has a partner of 4. So let me graph this. Right. So when you were graphing, when we were doing the vertical line test. Right, let me just do this. This is my y, my x values. Let me show you what that looks like on a graph. So 0 and 4. So 0 and 4 would be here. And then 0 and 2. So notice that if you were to do the vertical line test, right, as you pass this purple line, look, the purple line meets when it's on top of the x value, of 0, it also it touches the purple line at 0, 4 and at 0, 2. Let me give you another example. So when it's at 2, we have 2 and 4 right here. Make one more, and 2 and 5. So as this purple line moves, right, when you're doing the vertical line test, look, it fails right here because the purple line touches 2 points at the same time, at 2, 4 and 2, 5. So this is not a function. Not a function as the x value 0 and x value 2 have more than one output. Okay, right. Pretty easy, right? Page. Let's go to the next page. Now this is what we did today, Monday, right? We're describing here what's happening in the graph. So here's a situation. On each day, several tree leaves fall from the tree. One day, a gust of wind blows off many leaves. So first of all, let's look at the trees. Tree starts with leaves, so it's not going to start here. So if the graph started here, we could eliminate. But all these graphs, right? This is a tree. There's a certain amount of leaves. Here, there's a certain amount of leaves, and here, there's a certain amount. So they're all correct for now. One day, a gust of wind blows many leaves. So blows. So did the number of leaves increase? Well, this ain't the leaf increase when the wind blows. So this already out. So now we're left with B and C. So the gust of wind blows. You're losing some leaves. That's correct. And this one also says that's correct. But it says many leaves. So the decrease here should have been a sharp, steeper line. Well, they're both okay. Let's just let's say that they're okay. So they both lose leaves. Eventually, there are no more leaves on the trees. Well, eventually this line hits 0, right? Because there's no more leaves on the tree. Circle the graph that best represents the situation. So this is what happens. Wind blows, you lose some leaves. Sorry. Each day, several leaves fall from the tree. So here's a tree losing leaves, and then the wind comes and blows a lot. So there's a steeper line. And after the wind stops blowing, it still is going to lose leaves, so it loses at a lesser amount. I'm going to say this one. This says, hey, there's some leaves. Leaves are falling, and then here it says that no leaves fall from the tree. Right? That's why it's a straight line. It's a horizontal line. This is saying no leaves fall. So for a certain amount of time, no leaves fall from the tree, so which makes this incorrect. All right, take 3 vessels, fill them with water, fill this with water, fill this with water, and fill this with water. So this cup here, this is a cylinder, the same size, right? As it's filling, it's the same amount of water that's filling as it goes along. So this one has to be this one, right? Because it's filling the same amount. Whereas this one, think about how the water fills. First, it fills fast, and then it's slowing down because as the higher you go, the more water needs to be filled because the opening keeps widening. Whereas this one, as it goes to the top, right, as you're filling, so this one starts it starts fast, and then it slows down, right, because there's more water to fill, and as it's going up, it fills that faster because there are less, the opening, it starts closing. So this one, it starts slow, right? And then it slows down as it goes on top because it takes more time to fill. So this would definitely be B, this would definitely be A, and this one again starts a little bit fast and then slows down because look, as it's filling. This gets wider and wider and wider, and it takes longer to fill until you get to the top. Your oven. You turn on your oven to bake a casserole. Which graph best represents the oven over time? So, when you, the oven is not at 0 degrees. It's just not, right? The oven right now, if you go to your kitchen, right, there's a certain temperature, 50 degrees. You turn it on, what happens to the temperature? What happens to the oven? Temperature goes up, you put it, let's say you set it to 400 degrees Fahrenheit. It's going to warm up until it hits 400, and then it's going to stay there for, I don't know, the amount of time you're cooking the casserole. And then at this point, I guess, at some point, you take out your casserole, and then you turn off the oven, it goes down. This is the correct answer. So this one is weird, because it says here, temperature starts at whatever, 50 degrees, 60 degrees, it goes up, and then your oven goes up and down, the temperature. So it reaches, let's say, the desired temperature, 400. Then it goes down to 390, and then it goes up to 400, it goes down 390, up to 400, etc., etc. And the only way I can see this happening, if you're cooking and you open the oven, right, check on your casserole, and then you, obviously, as you open the window, the temperature decreases a little bit, and then you close the oven, and then you come back and you check it again, and you check your casserole 1, 2, 3, 4 or 5 times, and that would maybe explain the temperature here. As you open, your oven, you take the casserole out, check it, put it back in, close the oven, temperature goes back up, then you come back again, right? But it's not saying that, so I'm definitely going to select B. Okay, you can write the answer, explain your answer. The oven temperature, right, does not start at 0. At 0, okay. The oven is about I'm gonna say 60 degrees Fahrenheit. You turn it on, it rises to the set temperature, 400 degrees, 300 degrees, and then it cools down when you shut it off. Okay, so that is the story with that. Choose a graph that best represents the situation. Oops, what happened here? So it says a tomato plant grows taller at a steady pace. Well, steady pace means a straight line, like that. Right? It doesn't go grows tall, it grows at a steady pace, and then grows super fast, and then comes back at steady pace again. Steady pace means a straight line. So that's how you should read it. And then obviously, definitely, this one would be C. A tomato plant grows quickly at first, remain constant height during a dry spell, and then grows at a steady pace. Look at this one. Goes quickly at first, right? Look, it's steep, stays at the same height, and then grows slowly again. This would definitely be B. Tomato grows very slowly. Look, it's growing very slowly, and then all of a sudden, it grows quite fast with sun and water. So that would definitely be. Rebecca turns the oven and it sets at 300 degrees. She bakes a tray of cookies and turns the oven off. So where would that be? Right here. Like that, like this one. Remember, the oven is not at 0 degrees, so it's a certain room temperature. Goes up, bakes the cookies, she turns it off, and it goes back to room temperature. So definitely graph 3. I guess we can use these graphs repeatedly. Leon puts ice cubes in his soup to cool down before eating it. Okay, he does that. So remember that the soup, right, if it's hot soup, it starts at a high temperature. Look, soup starts like that. Put some ice cubes, the temperature starts going down, and then eventually it it's going to, I guess, stop decreasing temperatures. Just it went from hot to cool and stays the same. So I'm going to say graph 4. Barley has the flu and her temperature, so she has the flu. Her temperature should be high. And her temperature rises slowly until it reaches 101. Okay, so she has the flu. And then it reaches 101 and it stays at 101. So that would definitely be graph 1. On a hot day, Karen walks in and out of an air-conditioned building. Okay, it's hot. She goes in the air conditioning. What's her temperature? It goes down. Right? She cools off. Then she can't go outside. Her temperature rises. Right? She's walking outside, and then maybe she's gonna walk back in. So this would be the story. Um, 9. Which battle represents a person changing in height from birth to 80? Interesting. So this one says, let's look at B, that you are growing at the same rate for a while, for I don't know how many years. Grows, and you stay at the same height forever and ever and ever and ever. That's not true. I can tell you that for a fact. So you grow, you keep growing. It's definitely not at the same rate for sometimes you're small, you keep growing, and then you have a growth spurt, you grow super fast, and then once you reach your maximum height, right, you stop growing, and then, trust me, I guess, because maybe your shoulders start curving, you just get a little smaller as you get older. You do get small. Okay, you don't walk as tall as you used to, so it's definitely A. So explain your choice. Graph A, a person does not, right? We do not, does not grow at a constant rate. You don't grow, let's say, 1 inch per year until you're 18, or 2 inches, or whatever. Constant rate, right? A person does not grow at a constant rate, therefore, it is not linear. It's not a straight line, right? That's why I didn't choose this one. Okay. And as you get older, a little bit older than me, way older, you do lose a little height. Okay, that's for sure. Oh my God. The graph shows the distance Molly was from home, so she's walking out of the house. So she spent about 6 hours at school, 1 hour at a friend's house, 30 minutes waiting for a bus. She also walked and rode the bus part of the day. Use the graph to answer the following 2 questions. Which section most likely represents walking to the bus? Spent 6 hours at school. So this is what I would be. So when she's at school, her distance to home is the same. So this is the time she spends at school. 1 hour at a friend's house. She also walked and rode the bus part of the day. Walking to the bus would be right here. She walks to the bus, waits for 30 minutes. So this section here, walks to the bus. So section, oops, they have that line already. So section 1 would be walking to the bus. What section most likely represents spending time at a friend's house? Well, I would say section 6. because remember, when she's at a location and she's not moving, her distance to the house is the same, so we call that section 6. Which part represents Molly at school? Well, right here, the biggest chunk of time where the distance to her house is the same. So section 4 represents her time at school. Time at school, as it is the biggest chunk of time that biggest chunk of time where her distance to the house does not change, right? Yeah. Wendy's cup collection. Which statement represents this graph? Wendy's cup collection is decreasing over time? Definitely not. We know it's linear and we know it's increasing, right? So we know two things. It's linear and increasing. So so we know it's increasing because it's going up, right? So let me write going up. We know it's linear because it's a straight line, right? And what does that mean? That her collection has been increasing at the same rate, right? That's the same steady rate, right? So she collects 1 cup per week. It's always going to be at 1 cup per week. I'm making that up, but steady, at a steady rate. That's what it's linear, which means it's straight line, which means her collection has been increasing at the same rate. Wendy's cup collection is increasing over time. True. Check mark. Wendy's cup collection sometimes increases and sometimes decreases. Absolutely not. Wendy's cup collection remains the same size over time. No. So the only one that's correct is that's her cup collection. Look, it's increasing as time progresses. As the months progressing, her cup collection gets increasing at the same rate. Okay. Which situation is best represented by the graph below? So we have something that has something in it, and then it starts decreasing over time. So again, going down, let me just interpret this, means decreasing. It's linear because it's a straight line, which means decreases. What does that mean? Decreases at the same rate, right? So if you're, let's say, losing $5, you're losing $5 per day. So it's always $5 per day, so it's the same rate. But you don't start at 0, which means if we were talking about money, for example, you had $40 in your bank account, and then every week you use $5 per week. That'd be one story, for example. Okay. Now let's see what they talk about. The height of a child from age 10 to 15, absolutely not. It's saying that the height of a child here is decreasing, so this is definitely not it. The volume of a balloon as it being filled with air. Well, if you're filling a balloon with air, first of all, your balloon starts with 0 air, and it should be going like this, right? So that's not true. The amount of gasoline in a car's tank during a 5-hour trip. Well, of course. If you're going on a 5-hour trip, the first thing you're going to do is put some gas in your car, which means you start, I don't know, here with maybe, 15 gallons of gas. Let me just write that. And as you're traveling, what happens to the amount of gas that you have in your tank? It starts decreasing and decreasing. So this looks okay. The volume of water in the swimming pool as it's being filled. Oh, obviously not. So a swimming pool normally, if you're filling it from empty, it should be looking like this, right? Which is definitely not the case. It's being filled. It should have been increasing. This is definitely not. So C is the only right choice. And what do we have here? Which of the following graphs represent the person in the car driving and then slowing down for traffic driving at a constant speed and then slowing down again to complete stop. So if you first of all, I think we can even work back to complete stop. So this is, let me write time, and this is the car speed, yes? Right? So if it's going to complete stop, that graph should hit 0 right here. Should hit 0 right here. So right off the bat, this is gone, and this is gone. Okay, so here's a car driving, slowing down for traffic, driving at constant speed. Okay, so here's a car, right? So it's driving, slowing down, then it's driving at the same speed for a little bit, same speed, and then slowing down to complete stop there. This one says the car was at a particular speed, it slowed down to complete stop, like a stoplight, increase the speed a little bit, right? And then decrease the speed to a full stop. Definitely not the story that we're talking about. So C is the one that you want to choose. 3, Hank drove his cousin, who lives 150 miles away. He began driving at 4 p.m. Okay, the graph shows his progress during the trip. When did he stop for dinner? Well, here's his driving, right? He drove 25 miles, 50 miles. He's driving. So notice that from 7 p.m. From 7 p.m. to 8 p.m. This is 125. He's at 125 miles. He doesn't change. His distance, his miles traveled doesn't change. He's from 7 p.m. to 8 p.m. He's continuously at 125 miles, which means he's not driving here. He is at a stop. This is where he stopped at one of those places in the highway where you can grab a bite, right, from 7 to 8. Eats, stops, and eats, and then after dinner, he takes off again. So from 7 to 8 is our answer. I think we have one more. Oh yeah, the practice. Which graph represents an increasing function? Duh. Hopefully we selected this one. All right, increasing. Does it say linear? No, it doesn't say linear. Sorry, so this is an increasing function and this is an increasing function. So you got two answers. Why are those two? Because again, you can do the vertical line test. Right? So as you move the purple line, the vertical line across, notice that it is a function because it touches the purple vertical line in one spot. So does this one. Okay? It doesn't say linear, it says increasing function. This is an increasing function, and this is an increasing function. Okay, so both of them qualify. The graph shows the temperature of a liquid in a mug over time, which best describes the graph. So think about a mug, cup of coffee that you put, right? Here's a cup of coffee. What happens to the temperature? Well, first of all, it's hot. It's a certain temperature. And then temperature doesn't go up. It doesn't go down. What the heck? Hang on a second. The graph shows the temperature of the liquid in the mug over time, which best describes the graph of the function. The temperature of the liquid slowly increases. How is it? I'm not going to ask. Slowly increases and then slowly decreases over time. Okay, the temperature of the liquid quickly decreases. Well, definitely not. So first of all, it increases, right? So we go, it increases, and then it decreases. So anything that says otherwise, we can already eliminate. So the first one says slowly increases and then decreases. Oh, potential. B says it decreases first, so that's gone. C says the temperature of the liquid quickly increases and then decreases even faster over time. So notice that the rate in which it decreases is much slower than it increases. So this one is also gone. The temperature of the liquid quickly increases and then decreases more slowly over time. Yeah, that makes sense. Look, it went up fast in temperature, and then as it decreases, it did decrease, but not as fast as it increased. So definitely we have D. So this one is good. Three. The graph shows the amount of snow that fell each day over a 7-day period. I don't know why I can't read. And then hang on. What was the amount of snow day for day 2? So day 2 is this one, right? This is day 2. Right here's day 2. And what's the amount of snow? We get 1 inch. Okay. Second one, on which day was the snowfall 1.5 inches? On which day was the snowfall 1.5 inches? 1.5 inches. Well, 1.5 was this guy here on day 1, day 3, and day 4. Day 1, day 3, and day 4. Okay. Sorry, day 6, not day 4, day 6. What am I looking at? On day 6. And then, is the amount of snowfall a function of the day, or is the day a function of the amount of snowfall? Now, remember, this is your independent, and this one is your dependent. Right? Your x value is always the independent value, always. And your y is always your dependent. Okay, so the amount of snowfall is the function of the day. Okay, so the amount of snowfall is a function of the day. So I guess, I mean, this is kind of weird, but we can say, we can have two choices. Is the snowfall depends on the day, or is it the day depends on the snowfall? You gotta pick one, right? It doesn't make sense. The second one does not make sense. So definitely snowfall depends on the day, which makes the snowfall your dependent, or your x, your y value, and which makes it the day your independent, or your x value. 4, Andre's science class launching a model, okay, from a rocket from a picnic table. That's nice. So here is a rocket on top of a picnic table. That's why it's not at 0, right? It's on top of the picnic table, right here. Okay, little details. And what exactly is it asking us? And the graph represents a model rocket that's launched. Okay, so its launch, it goes up, it reaches its maximum height, and then at that point it turns around and goes back to Earth, and it hits the ground after 4 point something seconds. What is the height at which the model was launched? The model was launched at, what is this? 0 to, where are we going? I can't even see. 2, 4, 6, 8, 10. So each of these boxes on the y-axis goes by 2. So this is 4. Let's launch at 4 feet. It's on top of a table that measures 4 feet tall. Plot the point that represents the greatest height of the model rocket. So the model rocket, the greatest height is right here. And it's at this point where the rocket reaches high point and then turns around and starts going down. So that's the point 2, comma 64. Sorry, determine the point 2, comma 64. How long did it take? Well, it's, according to this book, it took 2 seconds. Right, and the second answer is 2 seconds to reach all the way to the top. Determine one interval when the height of the object was increasing. Well, it was increasing from 0 to 2. Right? So anywhere from 0 to 2, we can say that the rocket has been increasing. determine one of the interval when the height of the object was decreasing, anywhere from 2 to 2 to 4, 2 to 3, on any of these intervals, any from 2 to 3, 2 to 2.5, 2 to 4, 2 to 4 point, whatever that is, 4.1, it's decreasing. Okay. Number 5, the graph shows the temperature between 10 a.m. and 10 p.m. for one day at a city. Okay, when the input is 7, so again, if you should always write that this, your x is always your input. Remember, this is your output. Right? You can write that this is also your independent values. And these are always the dependent values. Okay, so it says when the input is 7, so when x is 7, what's the output? Well, when the x is 7, the output is, let me write, when x is 7, the output is 90. Okay, what does that tell you about the time and temperature? Well, it tells me that at 7 hours past 10 a.m., which would be 5 p.m., the temperature was 90 degrees. Okay, determine one time interval when the temperature was increasing. So anywhere from 0, right? So this is 10 a.m. by the way. That's when they start the clock. So anywhere from 10 a.m. to 11, 12, 1 p.m., 2 p.m., 3 p.m., 4 p.m., up to 5 p.m., the temperature has been increasing, right? But that doesn't say about time, so interval from 0 to 2, there. From 0 to 2, right here, it's increasing. Determine one time interval when the temperature is decreasing. So anywhere you pick from that here, any of this interval, from 8 to 9, from 8 to 10, from 8 to 11, I'll just write from 8 to 11, the temperature was decreasing. Okay. Last question, I think. Describe a real-world situation that would represent the graph labeled the axis. Okay. Let's call this time. Then this is distance from home. Okay, so here's Johnny. He is, I don't know. Maybe write this. dy is called the distance from home. Right, so he's at a library. Currently, the story starts that he's at a library. Okay, he stays at the library for however long this means, 2 hours, 3 hours, and then he starts walking home. So he's getting closer and closer and closer and closer to home. Okay. Or you can say, let me say another story. You're driving your car, so again, this is time, this is your speed, this is your y-axis, your x-axis. You're driving at a constant speed, at the same speed, driving, right, same speed, and then you start slowing down, right? And that's where your story ends. Okay. Let's see. 5 minutes. Another thing. Something that stays the same for a little bit and then starts decreasing. Time, bank account. Right, so I have money in my bank account. I don't spend any. Right, and then I start spending $5 per week as it goes down over time. Okay. Right, and it doesn't matter what, but as long as you really say that for this particular period of time, whatever you have stays the same and then starts decreasing at the same rate. So stays the same, right? And this one, because it's a straight line, linear and decreasing, you can say decreases at the same rate. All right, so make up a story where that applies. That's it. This will count as a quiz.